This is the fourth in a series of mini lectures introducing geomorphology. I'm going to go quickly, so use the pause and rewind buttons if you want to slow me down. We've seen before how landforms are created by processes that are controlled by physical forces. Today we're going to look at the force of gravity. A lot of geomorphology is about things being moved downhill by gravity, and although there are lots of different mechanisms involved, the same key relationship between stress, strength and strain applies to all of them. Gravity can be a driving force. Here it's pulling water over the Yellowstone Falls and pulling at a climber on the wall of the Devil's Tower. Gravity can also be a source of strength or resistance. For example, the strength of a dry stone wall comes from the force of gravity holding it down. Gravity controls the hydrological cycle, atmospheric circulation, ocean currents, and many other parts of the Earth's system. When a volcano shoots material upwards, gravity determines how long that material stays up and where it comes down. So gravity controls the distribution of the coarse and the fine debris around a volcano. It controls the processes of mass movement on the volcano slopes, and so it controls the overall form of volcanoes. At a smaller scale, the distribution of particle sizes in the scree slope behind the truck in the bottom picture is also controlled by gravity. Gravity plays a major role in determining the motion and deposition of land-forming materials. Any expression to explain rivers, lava flows, mass movements and most other geomorphic processes would have to include a term for gravity. Many well-known geomorphological relationships, like the one illustrated by the Hultstrom curve, lead us right back to gravity. But even though similar controls affect different phenomena, we do have to recognize that different things move downhill differently. In this picture of a supraglacial stream, the glacier and the water are flowing at very different rates and by very different mechanisms, even though both are driven by gravity. But the key relationship is always the same. A driving force or stress leads to a movement or strain, depending partly on the resistance or strength in the materials involved. Differences between things like rivers, glaciers and landslides, or even between different glaciers or different rivers, arise partly from the characteristics of the materials involved. For example, ice is different from water. These differences in material properties are often controlled by environmental conditions like temperature. For example, cold solid rock behaves differently from molten rock, and ice just below the freezing point is much softer than very cold ice. To see how gravity is involved in these processes, there are some important concepts we need to find out about. Shear stress is force applied parallel to a surface, like the force that makes a glacier slide over its bed. Normal stress is a force perpendicular to a surface, like the weight of that dry stone wall on the flat floor beneath it. Gravity acts perpendicular to a horizontal surface, but where the surface is at a gradient, gravity includes a component of shear stress parallel to the slope. As gradient increases, the shear component of gravity increases. Gravity doesn't make my pen roll across a flat tabletop because the force is all normal or perpendicular to the surface. But if I tilt the table, the pen starts to roll because now there's a shear stress. There are equations that let us work out the shear stress in different situations. For example, the shear stress driving ice motion in an ice sheet is given by tau equals rho gh sine alpha, or shear stress equals the weight of the ice times the gradient of the ice surface. Once we know the driving stress, we can calculate the strain, the movement. For the deformation of glacier ice, Glen's flow law says that the strain is controlled by the cube of the stress, which we've just calculated, times the hardness of the ice, which depends on things like temperature. Glacier movement depends on the applied stress, dominated by gravity and gradient, and on the strength or resistance of the ice or the glacier bed, dominated by things like friction, which also depends partly on weight and hence gravity. So gravity is a complex control because it affects both the driving force and the resisting force. To understand what's going on in this picture of contorted ice at the margin of the Greenland ice sheet, we need to think both about the forces driving glacier motion, the push on the ice from upstream, and the forces resisting movement, in this case the fact that the ice is frozen to the bed close to the margin, and the fact that the local driving stress is low because the ice is thin. The ice is being pushed from behind but held up at the front. It's like a big glaciological pile-up caused by geographical variations in basal shear stress and thermal regime. So to summarise, gravity acts as a driving stress encouraging downslope movement or deformation, but its effectiveness depends partly on strength or resistance offered, for example, by friction. Movement or deformation of materials by gravity can play a major role in geomorphic processes, and in another lecture we'll look at mass movements like landslides and avalanches to explore that idea in more detail.